Hello viewers, this is a small video on plastic hinge. In this video, we shall try to understand what is meant by plastic hinge, how to find the length of the plastic hinge, what are the other implications and the practical uses. Here is a bar which is having a fulcrum at A, which is a mechanical hinge. So hinge can be a mechanical hinge or a plastic hinge. In this slide, we are trying to understand what is meant by a mechanical hinge. So about this mechanical hinge, if I rotate the other end B, it will rotate. So if you give a small push upward, it will move. So this indicates the end A cannot carry any moment. That's why whenever we apply a lever arm and force at that, it produces a couple and it rotates the system. So this is a mechanical hinge. Another example is here a beam fixed at one end and hinged at other end. The hinge itself is a plastic mechanical hinge, and there is some intermediate hinge also, which is called internal hinge. So this also will not be able to carry any moment. Similarly, you can see a three-hinged arch having a hinge at the end A, B, and at the crown at C. So these all will not be able to carry any moment. This video is showing a mechanism made out of bars which operate on the principle of hinges. Again, here we see a window is opening and it is opening about the hinge. Now let us see how a plastic hinge is formed. For that purpose, we have considered a column here having certain height and a lateral load is acting. A lateral load is acting at top from the left. So as a result, on the left hand side, strain will be developed, tension will be developed, strain will be developed, and gradually, if the force increases or displacement increases, it may produce cracks like this. And with the increase of force or increase of deflection, the cracks will increase in number and intensity and in length, and more cracks. And some part of this may also spill out from the body of the column. Then it may penetrate inside the foundation also. Cracking may go inside the foundation, and finally it forms what is called a plastic hinge. So here, what happens inside the plastic hinge, it is giving you the maximum resistance possible by the section, where the steel has gone to its yield stress and the concrete has gone to its maximum permissible value as per the code. Let us consider a beam now which is hinged at the two ends, and a central point load is acting downward as shown here, and because of this there will be flexural bending moment set at the center. By the action of the bending moment, cracks will develop. These are the flexural cracks. With the increase of load, these cracks will increase, and it may also spill out at the bottom. And some concrete at the top may also crush because of compressive load. And finally, we see a full plastic hinge is formed in the beam at the center. Let us consider another example with a steel section. So we have a beam here which is fixed at the ends, and we have applied a central load. With the increase of the load, stresses and strains will increase, and finally it is forming a hinge here. The mechanism of formation is like this. When the load is less, it forms a stress diagram. At the top, compressive stress, at the bottom, tensile stress. Because it is steel, both the stresses are equal, and the stress is now less than the yield stress of this thing. But if we increase the load or bending moment at the center, then it will reach to a higher level of stress which is equal to the yield stress of the material. But only the extreme fiber has undergone this extreme stress sigma y, or the yield stress of the material. The other interior fibers are at lower stresses, as we see from the triangular variation of the stress. If we go on increasing the load, the stress will be going inside. This yield stress will be going inside more and more, and finally it will reach to the neutral axis. So this top block is called a fully plastic compression zone. Similarly, another plastic tension zone is formed at the bottom. So both these together forms a couple. The compressive force in the top block and the tensile force at the bottom block are at a distance of equal to Z, the lever arm. The lever arm is from the center of this top block and the bottom block, and from mechanics we can now find out the plastic moment of resistance for this section at the plastic condition. So it is half the area of this block, half the area of the whole section into the stress sigma y into the lever arm Z here. So this gives the plastic moment of resistance of the section, which is the maximum moment of resistance it can offer in its behavior, in its reaction. So this neutral axis is called also equal area axis because it divides the whole section into two equal parts. And from this principle it will be easy to find out the lever arm for this section. Now let us consider a concrete section. So as we have said, a plastic hinge offers maximum moment of resistance for a section. So a concrete section, this is the concrete section having some steel, and this is the stress block as per Indian standard IS 456. So it is a rectangular parabolic stress block having the CG here at 0.42x, and the compressive stress generated in the whole stress block is 0.36 FCK B x. X is the depth of the neutral axis. So if we apply this, force equal to 0.36 FCK Bx is the force, and lever arm is d minus 0.42x, because here up to here is 0.42x and d is the total depth of the what is called effective depth of the section. We are making a multiplier here 1.5 because 0.36 FCK B is for limited design strength, where the partial safety factor 1.5 was applied. So if we multiply this by 1.5, partial safety factor is eliminated, and this becomes the maximum plastic moment of resistance for the section. Incidentally, this is also the characteristic moment of resistance for the section. So as we are saying, in the plastic hinge, we are getting the maximum resistance in bending out of the section. Now there is a concept what is called the lump plasticity and distributed plasticity. Lump plasticity means we are considering hypothetically or ideally that the entire plasticity is located in a single point in the structure. This is the general assumption made by the different available software in the market which deal with the nonlinear analysis, because distributed plasticity, which spreads over a length, is difficult to model in the system. So this is the lump plasticity, and if we consider the length of the plastic zone, which is always having a definite length, not it is ideally it is single point, practically it is having a length. So if we consider the total length, it is called the distributed plasticity. Now let us see the difference between the mechanical hinge and plastic hinge. Mechanical hinge we have discussed in the beginning. We have seen some video also, and the plastic hinges just we have discussed. So what are the differences between them? A mechanical hinge cannot resist any moment. Once you apply moment, it will start rotating without offering any resistance. It offers highest moment of resistance for a section. So in the plastic hinge, it is offering the maximum moment of resistance against the external action. The mechanical hinge undergoes elastic rotation. It does not undergo plastic rotation because the system cannot carry much moment. But the plastic hinge, it undergoes plastic rotation. Mechanical hinge does not dissipate any energy because it is simply rotating without much action, whereas a plastic hinge dissipates energy through hysteresis. So a lot of energy will be dissipated through hysteresis. Energy is absorbed in the system from earthquake or wind, and it has to be dissipated, otherwise it will harm the system. So through hysteresis, plastic hinge will dissipate energy. That is another advantage of plastic hinge. Now plastic hinge length is there one concept, because the distributed plasticity is what is the real plasticity having a definite length. So here we have considered a column which has developed a plastic hinge at the bottom, because at the bottom the bending moment is maximum. So this red zone is plastic zone. Now this red zone also penetrates to a distance in the foundation below. So this entire length of the plastic zone is called the plastic hinge length, denoted by LP. The penetration of the plastic zone inside the foundation is called the length of strain penetration. Length of strain penetration given by LSP. So that is what we have written here. LP equal to length of plastic hinge, LSP equal to strain penetration length. Now the bending moment distribution and the diagram is like this. The real bending moment is given by blue color, which is parabolic up to the base, and the plasticity expressed in the form of curvature is like this. At this point, if you draw a linear up to the yield stress level, then the curvature of this, it is a moment curvature diagram actually. Right hand side is a moment curvature diagram. So at the yield condition, the curvature is the yield curvature up to here, phi y. And beyond that, whatever curvature you are getting is the plastic curvature, the plastic condition. This height is the plastic hinge formation in the member itself, and this height is the strain penetration length, LSP. The total length is the combination of these two, which is the LP. Now how to get the value of LP? In the literature, the values are available. For column or pier, it is LP equal to KLC plus LSP, which should be greater than at least 2 times the LSP. So LC, etc. we are discussing here. LSP equal to 0.022 Fy dB. Fy is the yield strength of the steel, and dB is the diameter of the bar. So Fy is the yield strength of the bar material. dB is the diameter of the bar in millimeter. So this unit is coming in millimeter unit. And K, the constant, is given by 0.2 Fu by Fy minus 1. Fu is the ultimate strength of the material of the river. Fy is the yield strength of the river. And this should not exceed 0.08. So with this formula, we are able to calculate the length of the plastic hinge of the system. Here LC, which is coming here, KLC, is equal to the length between the critical section to point of contraflexure of the member. For a pier, say a bridge pier, it is the height of the pier itself, which is equal to LC. Now plastic hinge length for shear wall having a different formula available in literature. So LP equal to KHE plus LSP plus 0.1 LW. LSP was there earlier also in the earlier column formula. K was also there. H is the effective height of the wall. So the effective height is to be calculated by considering the system to a equivalent single degree of freedom system, and therefore you can get the expression for effective height. LW is the length of the wall. So LW is the horizontal length of the wall. LSP is as earlier as we have discussed, and K equal to also as earlier. H effective length of the wall to be obtained from equivalent single degree of freedom system properties. Now plastic hinge we have discussed. So in the real field, how it looks like. So this is a model taken from SAP 2000 software for a building with 4-story height. So the beams and columns have formed plastic hinges. In the SAP 2000, the lump plasticity is considered, and these are given by small circles like this having different colors. The color indicate the amount of plasticity it has suffered, or plastic rotation it has suffered. So pink color is the lowest one, then blue color is the intermediate, and cyan color is highest in the scale of color. So different hinge formation in the members are shown here. Now how much is the plastic rotation theta p that a system can undergo? For taking a glimpse of this, we have taken one table from FEMA 356. This is a table for plastic rotation suffered by beam elements in the nonlinear analysis. So here small a, b and c are the modeling parameters in the diagram, which is not shown here. IOLSCP are the acceptance criteria, immediate occupancy, life safety, collapse prevention criteria. So for this criteria, what are the acceptance limits? LS and CP are again recurring here because these for secondary elements. These are. Now this table to be read by the steel ratio first. Rho is the tension steel ratio, rho dash is the compression steel ratio, and rho bell is the balance steel ratio. So this is the value given in the first column. Second column is the reinforcement, whether it is compliant or non-compliant. Compliant is C, non-compliant and C. Compliant means it is following the ductile detailing code of the corresponding country. So when it is following the ductile detailing code, we are telling it is compliance, and C letter is used here. Third column is the shear stress ratio. Shear force divided by width of the system into effective depth under root the strength of concrete. So based on this ratio, less than or equal to 3, greater than or equal to 6, 4 rows are given here, and the IOLSCP values are available here. So if we look at these values here, let us consider only a compliant building. Non-compliant buildings should not be used actually. These are old buildings which was designed prior to the code. So we can concentrate on the compliant buildings only. We see that the maximum value of the rotation here at the collapse prevention, it is almost at the verge of collapse. So rotation, plastic rotation is very high. The values are given in radian. So we see that the 0.025 is the highest in radian for plastic rotation for almost collapsing building. This value, if you take to degree, it becomes about 1.4 degree or so. So you can imagine at very small rotation, your system is collapsing. And for immediate occupancy, where building is health is good, and the life safety, where health of building is intermediate, the rotations are even lesser than those CP rotations. So at very small degree of plastic rotation, these are all plastic rotations, your system will lead to collapse. Thank you very much for watching the video. Subscribe the channel, like and share the video. You can put your inquiries in the comment box. I shall try to answer those. See you again in the next video. Thank you.